Hi everyone. Here we're going to talk about decision making under uncertainty and risk dominance. So, remember that in the assurance game between Aram and Bina, we were calculating the expected payoffs for each of the players. So, we saw that for Aram, the expected payoff of planting early was equal to P, the probability that Bina would plant early, multiplied by the payoff that Aram would receive when he planted early and she planted early too. So this was equal to 4 times P. And then we added that to the complementary probability 1 minus P multiplied by the payoff that he would receive if he planted early when she planted late. That was 0. So that was equal to 0 times 1 minus P. So this whole thing was equal to 4P. That's his expected payoff to plant early. We then also thought about his expected payoff of planting late. We saw that his expected payoff to plant late was equal to P multiplied by 3, the payoff that he received when he planted late and she planted early, plus 2, the payoff that he received when she planted late and he planted late, multiplied by the probability that she plant late. And that all equaled P plus 2 plus P, or P plus 2. Now, what we can do here is that we can think once more about this idea of maximizing your expected payoffs and preferring that strategy which gets you the higher expected payoff. So when thinking about this, we're going to use an idea that we call risk dominance. So the risk dominant strategy is the strategy resulting in the highest expected payoff when an actor weights the other player's two actions with equal probability. So what does that whole equal probability thing mean? Well, if they have two different strategies, the equal probability is to say, let's imagine that they played them randomly among those two, and they do it in such a way that the probability of each is 50-50. So we set P equal to 0.5. When we think about that, once we've set P equal to 0.5, having done that, we check which strategy produces the higher expected payoff. So that strategy will then be the risk dominant strategy. The strategy with the higher expected payoff when P equals 0.5 is the risk dominant strategy. Then, if both players play their risk-dominant strategies, the game has a risk-dominant equilibrium when both players play their risk-dominant strategies. Okay, so how are we going to think about this and how could we visualize it? Well, let's think about how to visualize our expected payoffs. So, along the x-axis, we have the probability that Bina will plant early, and that is equal to P. And so, as P goes from 0 to 1, we can see it's increasing there from 0 to 1. Now let's remember, what did we have for our expected payoffs? We had that the expected payoff, pi hat, and I'm just going to label that pi hat E for pi hat for planting early, that equaled 4 times P. And then we saw that pi hat L equaled 2 plus P. The expected payoff to plant late equaled 2 plus P. Okay, so the thing that we want to do now is we want to graph those two lines. Okay, so if we're thinking about playing the payoff to plant early and the payoff to plant late, what do we have to do here? What we should do is we should substitute in two values of P to understand what the intercepts would be at P equal to 0 and P equal to 1. Okay, so let's do that now. What we can see here is that for the 1, for P equal to for pi hat E, for P being equal to 0 or 1, when P equals 0, what do we have? Pi hat E equals 0. 4 times 0 is 0. When P equals 1, pi hat E equals 4 times 1, which is equal to 4. Okay, that's what we have for the two intercepts there. And if we sketch this line now, and we have an intercept up here equal to 4, and we look over here and we've got 1 equal to 0, we can draw a line going from 0 to 4. That would be the expected payoff to playing early. Now the other one that we have is plant late. So when P equals 0 for plant late, what do we have? We have 2 plus P. When P is equal to 0, that's equal to 2. 2 plus 0 is 2. Then when P equals 1, what do we have? Pi hat L equals 2 plus 1, that's equal to 3. So we can see here that we've got a line going from 2 to 3. And that would be the expected payoff to playing late. Okay, so what have we done now? We've just sketched the expected payoffs. We've we've found the intercept at p equal to 0 and p equal to 1. Having found the expected, the intercept when we have those different values, we just connect them as they're a straight line. They're just a straight line going from the one point to the other. Okay, so we can see that here, and I've got the expected payoff to playing plant late and the expected payoff to playing plant early. Now, there are a couple of relevant points that we're going to want to think about here. So let's think about these for now. Now, we know that pi hat e equals 4 times p. We know that pi hat l equals 2 plus p. So remember, what did we say? We wanted to understand what would happen when, what was true? P equals 0.5. What are the values of the different expected payoffs when the probability of each was equal to 50%? So, to think about that, let's just substitute the values in. When p is equal to 0.5, what does this become? This becomes 2.5. That's the expected payoff to playing plant late. With 4p, what does that become? That becomes 2. 4 times 0.5 is equal to 2. And we can even read this off the graph. So if we try to find p equals 0.5, which is approximately here, say that's p equal to 0.5, we can see that at that point, if we compare the values of the two figures, the two lines, the two expected payoffs, that we've got this one being equal to approximately 2 and this one being equal to 2.5. So if I could just sketch lines across, I could see that the values there are 2 and 2.5. What this then means is that planting late is risk dominant and planting late is not risk dominant. So what this means is that planting late is risk dominant and planting early is not risk dominant. So planting late is risk dominant because the expected payoff to planting late is greater than the expected payoff to planting early when the probabilities of each are 50%. Okay, so that's the one level of P that we're interested in, P equal to 0.5. But there's another probability that we're interested in, and that is called the indifference probability. Now, the indifference probability is the probability at which the expected payoffs for the two strategies is identical. Okay, so what we can see here is that there's one point here, point I, which is the point at which those two strategies are getting the same expected payoffs. So the expected payoff to playing plant early is equal to the expected payoff to playing plant late. So that happens when we have a very specific value of P. So what do we have to do in order to find that value? We have to find when the expected payoff to playing plant late is equal to the expected payoff to playing plant early. So what did we see there? Plant early, that expected payoff was 4p. Plant late, that was equal to 2 plus p. So we can set these two things equal to each other. Having set these two things equal to each other, what can we do? We can isolate p. So what you can see here by doing the algebra is that 3p will equal 2 by subtracting p from both sides, and that means that pi, the indifference probability, is equal to 2/3. That is this same indifference probability that we're seeing on the x-axis here. So when p equals 2.3, what does 2/3, what does that mean? It means that at that point, the players are indifferent between the strategies that they could play. If pi equals 2/3, what does that mean? It means that the expected payoffs are equal to each other at that point. So I can play early or I can play late, and if I play either one, I'm getting the same expected payoff in this game. So what we have to imagine now is that Bina is just one other farmer. That's how we thought about this in just Bina playing the different strategies with different probabilities. But another way of visualizing this is to think about the possibility of there being many, many, many other farmers who are just like Bina. And what we then have is a risk-dominant probability or risk-dominant proportion, and we also have the indifference probability being equal to a fraction or a proportion of the population. So imagine there are hundreds of farmers out there, and we think about what the other farmers do. Now, if enough of them are playing plant early, so more than 2/3 of them are playing plant early, what would that mean? It would mean we're in this region of the figure. So if more than 2/3 of farmers are playing plant early, what would that mean? It would mean the expected payoff to playing plant early was higher than the expected payoff to playing plant late. If less than 2/3 of farmers are playing plant early, it means we're in this region of the figure on the left-hand side. And what we can also see then is that when that happens, we're in the area where the expected payoff to playing plant late is greater than the expected payoff to playing plant early. If we're in that region of the figure, then players want to play plant early. What this also means is that we have another name for the indifference probability. The indifference probability, we can also think of it as what we call a tipping point. It is an equilibrium at which if there's a small change in what players do, we're either going to drive everyone to playing plant early, or we're going to drive everyone to playing plant late. So imagine we started off in a world where 2/3 of farmers were playing plant early and 1/3 were playing plant late. What that would then mean is if one additional farmer shifted from going to plant late to planting early, then plant early is now better for everyone. Everyone now wants to play plant early. PI has gone beyond 2/3, it's now 0.67. Being 0.67, now everyone wants to play plant early because we're at this point where the difference between the two expected payoffs is such that playing plant late, playing plant early gets you a higher expected payoff than playing plant late.